science. Welcome back, ladies and gentlemen, and here we are to do some work. Mashed potato, work. Yeah, we're going to do some work today, ladies and gentlemen. We're going to be talking about our topic, work and power. Today we'll talk about work. Tomorrow we'll talk about power. And Thursday we will do a little lab activity. So let's get right down to it and let's get to work. But I want you to, be thinking like a scientist here and ask yourself the question, what is work? I'd like you to pause me and discuss as a class. Okay, I'm back. And hopefully you had a good conversation about what work is. And I would like to take what you've said and add to it in the context of science class and start off with a demonstration. So I'm going to scoot over to our virtual lab here, and I'm going to give you a little demonstration. So here we are in our virtual lab, and we've got a countertop here, our lab countertop, which is not moving at all. And I've got a little feather here. Hopefully you can see the cute little down feather. Okay. I am going to do two things, example A and example B. And I want you to think about what I'm doing, and then we're going to discuss it after I show you these two examples. Are you ready? So pay attention. Here is example A, and think like a scientist. Example A. Whew, a little bit lightheaded there. That was example A. Hopefully you don't need to replay that. And now for example B. Are you ready? Example B. Woo! Okay, so example A, example B. Let's head back and discuss what we've seen. So here we are, and I'd like to ask you, as a class, the following question. In which example, A or B, did I perform more work? Pause and discuss. Okay. So what did you think? How many of you thought I performed more work with example A? Raise your hand. How many of you thought I did more work with example B? Now, you answered according to your understanding of what work is. But as you know, in science class, we have very specific meanings for certain words, and work is one of them. So let's define what work actually is. Work is a force acting through a distance. And I've underlined some words here. The word work obviously is underlined. The word force and the word distance. These are very key words when thinking about work. In fact, if you look at these words, I think we might be able to turn these words into a formula or an equation that we can use to calculate work. So work is. What do you think the word is means mathematically? Very good. Now, here's another phrase, acting through a distance, acting through a something. That phrase mathematically means multiply. So let's check it out. Let's see what happens if we put these words in the format of an equation. The equation is big W for work equals force times distance. And we can write out those words so that we know what the letters refer to. But work is equal to force times distance. And why don't we add the units here as well while you're writing these things down in your notes. The unit of force, as we know from last week, are newtons. And we know from previously the unit of distance we can measure in meters. And when you multiply newtons times meters, we end up with another unit in the metric system called joules. Now, not the kind of jewels that you'd put on rings or earrings, not those type of jewels. In fact, not even the type of joules that you would measure with the Troy measurement system, like precious metals and other jewels. This is a different type of joule. This is actually named after another scientist, James Joule. And the joules are simply a measure of work in newtons times meters. 1 Newton meter equals 1 joule. Now, I want you to think about those two examples I showed you at the beginning of the period. Example A and example B. Do you need me to show them to you again? Okay, I'll show them to you again. Our close-up view here in our lab. Remember, example A and example B. Whee! Okay, so let's head on back to where we were and think about this from a scientific point of view. I want to lead you to your understanding of this. In which example, based solely on my facial expressions, in which example was I exerting a greater force? In which example was I applying a greater force? Example A or example B? Everybody? All right, it's probably pretty obvious. We're not even using numbers here, right? You could see by my expression, I was in fact applying a much greater force. I was pushing as hard as I could down on that feather on the counter. Now, in which example did the feather move a greater distance? Example A or example B? Everybody? That's right, example B. In fact, how far would you say the feather moved in example A? If you said 0, you're absolutely right. The feather did not move at all when I was pushing down on it. It had nowhere to go. I certainly wasn't going to push it into the countertop. I'd have to be a little bit stronger to make that happen. So now think about the equation. Work equals force times distance. Think about this. In which example did I do more work from a science point of view? Tell me again, what do you think? Example A or example B? Let's look at it. In example A, my force was huge. I don't know what it was, but it was a big number. I almost bust a gut, pushing with an incredible force. In the second example, very little force was required to lift that feather. I have to be honest with you. In example B, I moved the feather, maybe 10, 15 centimeters or so. Not very far, but I moved it. But in example A, how far did I move it? 0. Laws of mathematics. What is anything multiplied by 0? Everybody. 0. So regardless of how much force I was pushing down on that feather in the first example, it wasn't moving anywhere. In other words, it had a 0 distance. And so it doesn't matter how hard I'm pushing, if it's not going anywhere, I was not doing any work. I could give you another example here. Let's see. Let's say you had a homework assignment that you had to complete, or an in-class assignment for that matter. And so you had a book or paper and a pencil or a pen, and you put your pencil or pen on one side of the paper, and it just stayed there all period long. You didn't move the pencil through any distance. Did you do any work? No. Here's another example. Let's say you were assigned to read something, maybe for science class or for another class, and you had your book in front of you, and you just stared at one of the letters, and your eyes did not move across the page at all. Were you doing any work? The answer is no. So as we talk about words and continue to talk about words in science, this week included, when we mention the word work, I want you to take it very literally and think about, well, all right, what is work? Work, force times distance. So now we're going to work on an example problem in your book. Because in your book, we are on topic 4, work and power. And in your notes, we have a little space for an example problem. And this is the example problem that we are going to use in that open space there. But I want you to remember those 5 steps for solving word problems. Remember a while back, you folded down one of the pages in your book. You can turn back there to refresh your memory about the 5 steps for solving word problems. As we look at this problem right now, it says, a student who weighs, and remember, weight is a measure of a force of attraction between you and planet Earth. So whenever you see the word weighs or weight, you know we're talking about a force. So a student who weighs, force, 500, and what do you think the N stands for, everybody? Newtons. That's right, 500 newtons. Now, before you start laughing, oh, who weighs 500 newtons? Man, they're big. Well, maybe not as big as you might think, because a newton is not the same thing as a pound. Talk more about that later. Okay? So a student who weighs 500 newtons climbs a flight of stairs 5 meters high. How much work is done? Take a moment, think about that question, and think about the 5 steps of solving a word problem. I'm going to ask you to pause the video now so that you can have a few minutes to work on it individually, and then we'll discuss it when you're all done. Okay, we're back, and hopefully you had time enough to complete this word problem using the 5 steps, beginning with the first step, and I'd like everybody to call it out. What do you do in the first step? Very good. We draw a picture. So now this is where you can be a little bit creative, have some fun. Remember that word problems, if they scare you, you want to bring some humor into the situation, because if you can make yourself smile or laugh, it increases blood flow to the brain, and it will make you think more clearly and think better. So, draw yourself a picture. With me, I'm just going to draw a little stick figure. A stick figure that looks like his head is going to actually fall off his body, perhaps. But I have drawn a picture of someone climbing up a flight of stairs. So far, so good. You've already got a point, and you haven't done any math here yet. All right. Second step in solving word problems. What is it? Everybody. TOV, or table of values. Yes, your table of values is a list of what you know and what you are looking for. So when you prepare your list in your table of values, I want you to remember to use the letters that we're learning about in class to help you with the next step. So, who can share with us your table of values? Hopefully, you gave the following information. Capital F for force. Remember, weight is a force. Force is equal to 500 newtons. That's your first piece of information that you read as you're going through this word problem. Weight, or weighs, 500 newtons. You write it down and remember that the capital F is for force. The next piece of information you can see is 5 meters high. The height of something is a measure of distance. So distance is equal to 5 meters. And the question is asking you about the work. So capital W for work is equal to a question mark, because that is the question. We don't know how much work is being done. That's why we have to do this problem to calculate it and figure it out. But please make sure that when you are writing your table of values, you use the appropriate letters, because it will help you with the third step of solving word problems, which is what? Excellent. The third step is to determine the correct equation that you need to use in order to solve the problem. So, if you look at your table of values, F, D, W, and look up in your book on your notes page right above where we are right now, you should see an equation. In fact, right now, why don't you put a box or a circle around that equation to help it be highlighted in your notes so that you can study it this week. But you should have the equation in your book that reads big W equals capital F lowercase d for work equals force times distance. And remember from previously, there are a number of different ways you can express multiplication between two or more variables. So here are two variables right next to one another with no space, indicates multiplication. All right, we've done 3 steps. What is step 4 of solving the problem? Everybody. Plug it in, plug it in. Plug in the values, or PIV. And when you plug in the values, remember, you're rewriting the equation, but instead of the letters, if you know what those letters represent with numbers, you're going to plug in these numbers into where the letters are. So when you plug things in, you've got big W for work is equal to 500 newtons times 5 meters. I'm just writing the numbers down here to make things a little bit simpler for you to follow. but remember they do have units, newtons and meters. And that brings us to the only step of the 5 steps that involves actual mathematics. And so what is that 5th step of solving word problems, everybody? The solution, or solve that problem. You've got to solve it to find the solution. So here we just do the math. So what is 500 times 5? Think about it. 5 times 5 is 25, and there are 2 zeros there. So our answer is 2,500 Newton meters. Now, if you think about earlier in your notes, what is a Newton meter? What unit is used to express a Newton meter? Everybody. Excellent. So your answer is 2,500 joules. 2,500 joules is the correct answer for this problem, and it might not mean a whole lot to you yet, but I'm going to tell you something. When we pick this topic up tomorrow and work with power in addition to work, you're going to see how much work this really is. But for today, I just want to take it one step at a time, and I'm going to give you some practice examples now on the rest of this page that I would like you to take some time working through for the remainder of the period, and we can discuss them later. So for the remainder of our time together, please work on the practice problems on page 49. We'll talk about them later, and for now, I'll say bye-bye.